All right, let's get started with this SI sheet. We are in the carboxylic acids derivatives chapter. And unfortunately, there's a whole bunch of carboxylic acid derivatives. There's five you learn about in the book. So we have to learn how to name five different things. In terms of reactions, we'll probably see the least amount of reactions with the nitriles, though. But we still should be able to name all of them. So starting with the acid chloride. You should always start numbering at the carboxylic acid derivative. So we're going to start numbering at the acid chloride. 4, bute. We have an alkene on carbon 3, so we're going to signify that. And then normally we'd end it in ene, but because we have an acid chloride, we're going to end that part as OYL, like ol, and then space chloride. We're kind of naming this as a substituent for the chloride. And that's how you just name acid chlorides, is do the parent chain, end in OYL, and then end it space, and then end it in chloride. So that's naming acid chlorides. Naming anhydrides. To name anhydrides, you have to name each side of the anhydride separately, unless it's symmetrical, and in that case, they'd get the same name, like this is symmetrical. But we don't have that case here. It's an asymmetrical. So we're going to number each side separately. On the left side, we have 2. 2 is an F group. So right here, F. We don't have any alkanes or alkenes. So FN. And then we end each side of the anhydride in oic. So this is going to be ethanoic. And that's it for the left. For the right, we have 3. So we can put prop, no alkenes or alkynes. So propan, and then we end it in oic, like I just talked about. We have a substituent on carbon 2. We have a fluoro group, so we're going to want to include that in the name as well. And it's on carbon 2. And then we have a chiral center, so we have to determine RS. So fluoro gets 1. This gets 2 since it has the carbonyl, and then 3. If you draw from 1 to 2 to 3, it's R. So we're going to include that in the name as well. R in parentheses. And let me space this out a little bit better. Because there should be a space in between each of these two sides of the there should be a space in between the two sides of the anhydride. So we named each side of the anhydride separately with a space in between them, and then we're going to end the full name in with anhydride at space anhydride. And the reason I put the ethanoic in front of this long one is alphabetical. So E comes before P in the alphabet, so that's going to come first. And what I mean by alphabetical is alphabetical of the like carbon chain. So the carbon chain is eth, and then this carbon chain is propyl. That's how you order them. So that's how you name anhydrides. Name each side with oic at the end, and then space in between them, and then space anhydride. All right, let's name the amide. Remember, always start numbering at the carboxylic acid derivative. So 1, 2, 3. And then we're also going to number the substituents coming off of the amide separately. So here we have 2 and here we have 1, but we'll get back to that. I'm jumping a little ahead. Let's first name this carbon chain. So 3 is prop. No alkenes or alkynes, so propan. And then the way you end in amide is really easy. Just amide. And that's it for that side. but we still have to name this ethyl group and the methyl group. And the way you name these substituents coming off of the nitrogen is actually pretty easy. You just treat them as normal substituents. And I'll show you what I mean by that. So here we have an ethyl. So we're going to include that in the name, ethyl. And then instead of putting a number like we normally would when it comes off of the carbon chain, to signify that it comes off of the nitrogen, it's really easy. You put an N. And this N should be italicized. So I'm going to add some curvature to it. But you wouldn't have to emphasize that on the test. So that's the ethyl. And now we have to include the methyl. So let's include the methyl in the name. And we have to indicate it's on the end, so it should be like that. See if you can point out my error. I'm sure you were able to find that this should have come before the methyl. So let me swap them two around. That did not end up working. That's okay. At least this one is working. Okay, I'm just gonna rewrite it. So then the ethyl should come before the methyl because of alphabetics, of course. So this is the complete name. N-ethyl, N-methyl, propanamide. That's how you name amides. Name the carbon chain normally, add amide at the end, and then whatever comes off of the nitrogen, just treat as a substituent, but instead of putting a number like we normally do when it comes off the carbon chain, you add an N to signify it comes off the nitrogen. Okay, next one. Let's name the ester. So to name the ester, we're gonna first number coming off of the carbonyl group. And we're going to, let's start off with just that to begin with. We have 3. 3 is prop. No alkenes or alkynes, so propan. And then the way you end, or the ending for esters is O8. So propanoate. And that's it for that side. For the chain coming off of the oxygen part of the ester, we first number it as if it's its own chain. 1, 2, 3. That's prop. Prop. We have an alkene on carbon 2, so propene. And then the way we name whatever group comes off of the oxygen is we treat it just as a substituent, so YL. So prop 2 enol space propanate. That's how you name esters. The carbon chain that comes off the carbonyl is the ending with O8. And then the part that comes off of the oxygen part of the ester is treated as a substituent, and then the ending YL, like if it was a substituent. All right, last one. Nitrile, probably the easiest to name. So we're going to start numbering at the nitrile. 1, 2, 3, 4. 4 is bute. Now, coming off of the nitrile, we don't have any alkenes or alkynes, so we're going to do butane. So when I'm saying we don't have any alkenes or alkynes, we ignore that triple bond. And actually, technically, an alkene or an alkyne is a carbon-carbon bond. So this wouldn't even be considered an alkyne. But I was more looking for not including that triple bond of nitrogen. We don't have any alkenes or alkynes, so that's why it gets the A as opposed to a Y. And to name nitriles, you actually do keep the E. I know normally we would always take off the E when we end whatever functional group we're naming. But for nitriles, you do keep the E at the end. So this is gonna be butane, and then to signify it's a nitrile, you end it in nitrile. Pretty easy. So butane nitrile, and then we have a carbon, or we have a methyl group on carbon 2, so we have to include that in the name as well. And that's coming off of carbon 2. We have to determine RRS. So what's number? Triple bond will get 1, methyl 2, and then methyl 3, 1 to 2 to 3. No flip is R. So we're going to include that in a name. So we have R2, methyl butane nitrile. To name nitriles, name the carbon chain normally with the E and then just end it in nitrile. All right, now we have to determine which of the derivatives is more reactive. If you remember from the last test, anytime we have a carbonyl, Dr. Mullins wants you to draw the Zwitter ion. So we're gonna do that. Draw the Zwitter ion. So pushing the electrons onto oxygen. And then we're gonna do it for only one of the sides of the anhydride here. So I'll do the left. Like that. So now we have to determine which of these two Zwitter ions is more stable. And that helps us determine which one is more or less reactive as well. So if you remember, chlorine is a very electronegative atom. So although it can do resonance, chlorine doing resonance, let's just show it. Come on. Doing resonance, come on. Would put a double bond on chlorine and give chlorine a very electronegative atom a positive charge. So that would never happen. So we can ignore that resonance structure. And then if you remember chlorine, because it's very electronegative, it is going to have a strong dipole going that way. And let me try to emphasize that. And by having a strong dipole going that way, that makes this positive charge even more positive. So that's pretty unstable. And now let's look at the right. This oxygen can do resonance, and it's more likely to do resonance than the, than the chlorine. Because oxygen can handle a positive charge better than chlorine can. But oxygen is still pretty electronegative, so it doesn't really ever want to do that resonance structure. And oxygen itself is also pretty electronegative. So it's going to have a pretty big dipole here as well. But because I shouldn't have erased the resonance structure, but because oxygen is more willing to do that resonance structure, that makes this molecule more stable than the acid chloride. Because although oxygen is pretty electronegative like chlorine is, oxygen is more willing to do this resonance structure than chlorine is. So because of that, the anhydride is more stable, and more stable means less reactive. So that means that the acid chloride is more reactive. To give that a quick summary, the acid chloride is more reactive because it's less stable, and it's less stable because the chlorine, an electronegative atom, is going to make that positive charge even more positive, and it doesn't want to do resonance. But here in the anhydride case, although the oxygen is electronegative like the chlorine, it's more willing to do resonance than the chlorine, hence making that positive charge more stable. All right, let's do the same thing for this next one. We have an ester. So let's draw the Zwitter ion. Like that. And then we already drew the Zwitter ion for the anhydride, but I'll redraw it anyways. And remember, we're only doing one side. Yes. So here we have, unlike the previous example where we had a different heteroatom, we had a chlorine versus an oxygen. Here we have two oxygens, and the only difference is this oxygen on the right has a carbonyl, where this one on the left doesn't. So we can't really compare the electronegativity of the two because they're both oxygens, so I'm just going to erase that typo. So what we have to look at is resonance. So this ester can do resonance here in order to stabilize that positive charge and put a double bond right there. So that stabilizes the positive charge because you can move the positive charge on the oxygen. And you might say, but the anhydride can do that too. And you are correct. The anhydride can also do that. And I already drew that, so save time. Show that. So that's not the difference because both of them can do resonance onto that carbon in order to stabilize the positive charge. The difference is, which you can maybe see, you probably see, is that this anhydride can also do resonance onto this side. It can do resonance onto the other side of the anhydride. So let's draw that. So that creates another positive charge on that oxygen and a negative charge on that oxygen. So how stable is this resonance structure actually, though? We went from 2 charges in this molecule, and now we have 4 charges in that molecule. So does that resonance structure help? No, it doesn't help at all. But actually, this oxygen will maybe sometimes do resonance into this structure. And because it'll sometimes do resonance into that structure, it's going to sometimes be in a way more unstable state than this other resonance structure, hence making the anhydride less stable and more reactive. That's one explanation to go about it. Another explanation is we only want this oxygen to do resonance with this carbon. We don't want this oxygen to do resonance with the other carbon, like in the anhydride. And the reason for that is because we want to stabilize this positive charge. We don't want to stabilize this right side of the molecule, only this positive charge. By the anhydride having the ability to go to the other side, that creates the how do I want to word this? That makes it so that this oxygen is also doing resonance on the right side, even though we only want it to do on the left side. Where in the ester case, this oxygen is only going to do resonance with the left side because there's nothing on the right side. We only want the like ether or center oxygen to do resonance on the left side and never on the right side. And that is why the ester is more stable and that this is more reactive. This oxygen will do resonance on both sides, even though we only want it to do it on the left, where this oxygen is only going to do resonance on the left side like we want. All right, next one. We're going to do an ester versus an amide. So draw the zwitterion. I already drew the zwitterion for the ester, but I'll redraw it. And then let's draw this zwitterion. Both of them can do resonance. We have the resonance structure already drawn for the ester. And then the nitrogen, this should be N2, H2, and H2 rather. This nitrogen could do resonance here as well. And if we draw both these resonance structures out, nitrogen is more willing to take on a positive charge than oxygen here. So because nitrogen is less electronegative, it's more willing to take on a positive charge. That makes this resonance structure more stable than That makes the amide resonance structure more stable than the ester resonance structure. Hence, the amide is more stable and the ester is more reactive. So more reactive. So that's more. Let's do that. And I can just erase this. So those are the answers. Okay. Next one. Based on your answers, rank them. So we can, since we already relatively ranked each of the groups, we can just put them all on one list. So the acid chloride we said was more reactive than an anhydride. And then we said an anhydride was more reactive than an ester. And then an ester we said was more reactive than an amide. So increasing reactivity, actually right, increasing. And then if something is more reactive, that means it is less stable. So then stability, the stability arrow is going to be going the other way around. Like that. All right, next one. Reach at the circle, correct answer. Is it easier to synthesize reactive molecules starting from less reactive or synthesize less reactive molecules starting from more reactive? So what this is asking is it easier to, the first scenario is saying we start from a less reactive molecule. So start with low energy and then synthesize a more reactive molecule. Something that's very reactive has a lot of energy. So the first scenario is trying to go from low energy to high energy. And the second option is starting from a more reactive molecule. So starting from more energy and going to a less reactive molecule. Less reactive means less energy. So that's what it's asking. Is it easier to go from low energy to more energy or more energy to less energy? And if you know from the first rule of organic chemistry, the ball rolls downhill. It is always easier to go from high energy to low energy. So it's going to be the second one. So given that, what would be easier to perform? Synthesize an acid chloride from an anhydride or the vice versa, synthesize an anhydride from an acid chloride. Remember, let's think about this from an energy perspective. We want to go from more energy to less energy. If we scroll up, the acid chloride has more energy than the anhydride because it's more reactive. So because the acid chloride has more energy than the anhydride, it'd be easier to go from the acid chloride to the anhydride because the chlorine has more energy than an anhydride. So it'd be easier to synthesize an acid chloride starting from an anhydride, starting from low energy, or starting, wait. I think maybe I messed up. Maybe I messed up my wording, but no, it should be the second one. That it's easier to synthesize an anhydride starting from acid chloride because it's easier to start with something with high energy than go to something with low energy than the vice versa. Acid chlorides are more reactive than anhydrides, so it's easier to start with something with a lot of energy and end up with something with less energy than the starting material. All right, next one. Synthesize an ester starting from an anhydride or synthesize an anhydride starting from an ester. So once again, we're going to look at how much energy each has, ester and anhydride. The anhydride has more energy than the ester. So because of that, it's easier to go from an anhydride to an ester than the other way around because the ester has more energy than the ester because it's more reactive. So it's easier to synthesize an ester starting from an anhydride because what we're starting with, the anhydride, has more energy than what we end with, the ester. Acidic conditions. If you remember, negative charges should never be made in acidic conditions. And whenever we use acidic conditions, think sulfuric acid and water, we create H3O plus. That's a positive charge. So should be the first one. And then basic conditions, acids and bases are opposite. So if in acidic conditions you use positive charges, basic conditions, you're going to use negative charges. And positive charges should never be formed. All right. We're going to do some reactions. First, I would want you to identify whether these is acid or basic conditions, because that's going to determine the mechanism. Because we have an ionic bond, we have charges. Charges means basic conditions. And because we're in basic conditions, we are not worried about forming negative charges, but we're worried about forming positive charges. We want to replace this chlorine group eventually with a hydroxyl group. So we're going to need to attach this hydroxyl group to this carbonyl somewhere in the mechanism. Because our hydroxyl group and the NaOH already has a negative charge, it already wants to react and attack the carbonyl. Because negatives attack positives. It's going to attack this partial positive on the carbon. And then that'll push the electrons onto the oxygen. And that's going to create a negative charge on the oxygen. But remember, we are in basic conditions. We're not worried about a negative charge. We just shouldn't form a positive charge. So now we added on our hydroxyl group onto the carbon. But we don't want, so what's separating us from where we are in the product is we don't want this chlorine group here anymore. And we need to form a double bond between this carbon and oxygen. Chlorine, if you remember, is a good leaving group. So a good leaving group can leave. And at the same time, we can have oxygen drop its electron down, drop its electrons down to create that carbonyl, and at the same time have the good leaving group leave. And that would take us from an acid chloride to a carboxylic acid. You'll find you probably are going to like basic conditions a lot more than acidic conditions because they're a lot quicker. Here, you see we have sulfuric acid. Oh, what just happened? There we go. Here we have sulfuric acid. So because we have an acid, we're in acidic conditions. Remember, in acidic conditions, we can never form a negative charge, but we can form positive charges. This is ethanol. It's just written kind of funky. So let me redraw it like that. So you'll see we start with an anhydride and we want to finish with an ester. So we have to remove that part of the molecule and we need to replace it with an ethanol group. Because if you look, these two look exactly the same. So in the mechanism, we're probably going to have this ethanol attach itself to one of the carbonyls and then kick off this group. So that's what we want to do. We want this ethanol to attack the carbonyl so we can eventually kick off this group. But because we're in acidic conditions, this would, one, create a negative charge on the oxygen, which we don't want. And also, alcohols are poor nucleophiles, so this is never going to attack a carbonyl. And we learned from the last test, in order to make a carbonyl more electrophilic for a poor nucleophile like an alcohol, is we can protonate. Protonate that carbonyl oxygen to make it more electrophilic. So that's what we're going to do first. Just protonate that oxygen. And now we have just made this carbonyl a lot more electrophilic, which allows a weak nucleophile like ethanol to come in and attack the very electrophilic carbonyl. And let's draw the result of that. And then we have an alcohol group coming up now. So we have a positive charge on this like ethanol group. So let's remove that positive charge. And push the electrons back on the oxygen to remove the positive charge. And then now we still want this group to leave. This is a pretty decent leaving group because if this would leave, yes, we would have a negative charge, but this can do resonance. So this isn't a bad leaving group. But the issue is we are still in acidic conditions, so we can't just have this leave because that would form a negative charge. So to avoid a negative charge being created, we can protonate it first. And that makes this an even better leaving group also. So the result of that is now we have a protonated anhydride, an even better leaving group because it's a positive charge. And what's a good leaving group going to do? It's going to leave. And then we want to form a double bond between that this oxygen and this carbon because we have a carbonyl in the products. So at the same time, we can form our double bond. And we know it's not a double bond with this oxygen because this is our ethyl group on the ester. So draw the result of that. We have a positive charge, and then what's separating us from where we are in the product is just we need to take a hydrogen. And that is the complete mechanism to go from an anhydride to an ester in acidic conditions. And then earlier we showed how to go from an acid chloride to a carboxylic acid under basic conditions. Let me know if you have any questions. Feel free to text me.